Hello everyone. So, this is the fifth lecture of week 7. Recall that in the previous 4 lectures we learnt about quadratic penalty method. We learnt how to construct the quadratic penalty function for when you have only equality constraints and when you have only inequality constraints, and we also gave a sample code for certain examples which has only equality constraints and only inequality constraints. Okay. To complete this, we will also see what happens, I mean what would you do when you have both equality and inequality constraints, right. So, I mean this was the problem that you had initially, right. So, if you recall, so yeah, this was the problem that we had, where you had you are minimizing f of x subject to p inequality constraints and m equality constraints, right. So, what when you just have this particular problem, what is the quadratic penalty function? The quadratic penalty function for both. So, I will write it as equality and inequality constraints. So, yeah, in that case q of x comma gamma is actually f of x plus gamma into summation j equal to 1 to m h j of x the whole squared plus summation I equal to 1 to p g a of x plus the whole squared. Okay. Recall that g a of x plus means max of 0 comma g a of x. Okay. So, I mean this is nothing new, you just need to I mean add up the penalties of all the constraints. Okay. So, whenever a particular equality constraint is not satisfied, you levy a penalty of gamma for that particular constraint, and whenever an inequality constraint is not satisfied, that is j of x becomes greater than 0, then again you levy a penalty of gamma based on the value of j of x plus, right. So, and the rest is the same, and when you want to write a code for when you have both equality and inequality constraints, right. So, that is going to be very simple. I will just indicate this so that you get you understand what is happening. So, when you have only inequality constraints, you just defined f g grad g and you went ahead. When you had only equality constraints here as in here, so you defined f h grad h and went ahead, right. So, when you have both equality and inequality constraints, you have to define h grad h, g grad g, and I mean define q grad and h accordingly. So, you will have h of x dot h of x plus g of x into 0 in g of x greater than 0 into g of x dot g of x. Okay. And similarly, you will have in grad of x you will have del f of x and this plus what you had for inequality constraint, and in h you will have this plus what you had for inequality constraint. Okay. So, I mean one thing is you can notice so h of x actually will have, so this is the Hessian of f, this is 2 into gamma into del h of x into del h of x transpose, right. You will also have 2 into gamma into h of x into the Hessian of h of x. Okay. So, since in all the examples that we considered the Hessian of h is actually 0, right. So, that was the reason why I mean that term did not occur, but I mean when you write down a general problem you need to write it carefully, write the q grad and h even more carefully. Okay. So, yeah, I think that I mean yeah, I can also work out an example, but I think I mean it is not very hard, given that I have worked out examples for equality constraints separately, inequality constraints separately, right. So, when you have both equality and inequality constraints. Okay. So, we will go ahead regarding the analysis of quadratic penalty method, okay, instead of considering further examples. Okay. So, yeah, let us say if you recall the method, the algorithm, right. Yeah, so here is the algorithm, right. So, you first initialize x 0 and k equal to 0, you set the tolerance and you find a gamma 0, gamma 1, gamma 2, which is an increasing positive sequence and it diverges to infinity, right. And yeah, so while this constraint is satisfied, mod q of x k gamma k minus f of x k greater than tolerance, right. We find the value of x that minimizes q of x comma gamma k, and yeah, this continues until yeah, the difference between q of x k gamma k and f of x k is less than the tolerance, and we output x k as the minimizer, right. So, there is an inherent question, why should this method actually converge to the right answer, right. So, yeah, I mean we have seen quite a bit of examples where it actually converges, right, but is there a proof to say that this method actually converges, and are there some properties of this method that we can understand what regarding what is going on. Yeah, if we did something and it gives the answer, that much is fine, but I mean can we have an understanding of what happens in each iteration and so on, right. So, I will actually give a theorem which tells you what actually happens. Okay. So, the theorem is as follows. So, for quadratic penalty method we have, okay, for quadratic penalty method we have 3 results. One is q of x k gamma k is less than or equal to q of x k plus 1 gamma k plus 1. The second is the penalty of x k is actually greater than or equal to the penalty at x k plus 1, and the third is f of x k is less than or equal to f of x k plus 1. Okay. So, what this theorem tells us is, I mean it basically compares what happens between successive iterations. So, these iterations are of outer loop, okay, not the inner loop. Okay. So, that is, so take the value of q, that is, okay, q is the yeah, the quadratic penalty function that we are minimizing, right. So, the value of q keeps on increasing as we move ahead in the iterations. The value of the penalty keeps decreasing as we go further and further into the iterations, and the value of the objective function keeps increasing as we go further and further into the iterations. Okay. So, yeah, I mean if you are wondering what is penalty, so it is just that q of x comma gamma is f of x plus gamma into p of x. Okay. So, since there could be many constraints, many equality and many inequality constraints, right. So, p of x is just so if you just see above, you have summation h j of x the whole square plus summation j of x plus the whole square, that is what is p of x in simple words. Okay. The penalty actually. So, q is actually the objective function plus gamma into the penalty. Okay. So, what the theorem says is that q increases in successive iterations, f increases in successive iterations, but p decreases in successive iterations. Okay. So, I will prove this, I mean this is not very hard. Okay. So, yeah, recall that x k is actually the argmin over x q of x comma gamma k, right. So, I mean that just follows, yeah, here the ticked equation, right. X k is just argmin of x argmin q of x comma gamma k, right. So, what that means is that q of x k gamma k is less than or equal to q of any other maybe x bar comma gamma k, right. So, that is why it is the minimizer, right. Yeah, so, we will use this. So, note that q of x k plus 1 gamma k plus 1 first equal to, yeah, f of x k plus 1 plus gamma k plus 1 p of x k plus 1. Okay. So, this is actually greater than or equal to f of x k plus 1 plus gamma k p of x k plus 1. So, that is very simple because gamma k plus 1 is greater than gamma k, okay, and p of x k plus 1 is obviously non negative, right, it is the sum of squares. So, when you substitute gamma k plus 1 by gamma k, I mean the left hand side is greater than or equal to the right hand side, okay. But note that, I mean from this equation we have this to be greater than or equal to f of x k plus gamma k p of x k. So, that just follows from q of x k gamma k less than or equal to q of x k plus 1 gamma k, right. So, I mean you can put anything here, here I have put x k plus 1, okay, and this is just q of x k gamma k, okay. So, you can see that q of x k plus 1 gamma k plus 1 is greater than or equal to q of x k gamma k, that is the first result, okay. And yeah, we will now prove the second result, p of x k greater than or equal to p of x k plus 1, okay. So, if we use this equation for x k, we will have f of x k plus gamma k p of x k is greater than or equal to f of x k f of x k plus 1 plus gamma k p of x k plus 1. So, this is just, I mean instead of x k, if I substitute x k plus 1, sorry, this is less than or equal to, yeah. So, yeah, because this equation is minimized at x k, right. So, this is going to be less than or equal to, and if I do the same for gamma k plus 1. So, I will have f of x k plus 1 plus gamma k plus 1 p of x k plus 1 is less than or equal to f of x k plus gamma k plus 1 p of x k, right. So, again I mean this is the minimum because the equation is minimized at x is equal to x k plus 1, right. Now, if you add these both, okay, so you have f of x k plus f of x k plus 1 plus gamma k p of x k plus gamma k plus 1 p of x k plus 1 is less than or equal to f of x k plus f of x k plus 1 plus gamma k p of x k plus 1 plus gamma k plus 1 p of x k, okay. So, you can cancel these two, okay, and if you bring this here you will have gamma k minus gamma k plus 1 into p of x k minus p of x k plus 1 less than or equal to 0. So, if you are wondering how this occurred, you can multiply gamma k p of x k plus gamma k plus 1 p of x k plus 1 and minus gamma k p of x k plus 1, that is what comes when this is brought to the left, and this is minus gamma k plus 1 p of x k when this is brought to the left, okay. So, we know that this is less than or equal to 0, or less than 0 in fact, because gamma k plus 1 is greater than gamma k. So, this has to be greater than or equal to 0. So, therefore, we have p of x k greater than or equal to p of x k plus 1. Okay. So, that is what we have to prove. So, we have proved the second part as well. Now, the third part is f of x k, I mean this is something we need to prove, f of x k less than or equal to f of x k plus 1, right. So, here you have yeah. So, we again to prove this we start from this same equation that we have here, f of the topmost equation, f of x k plus gamma k p of x k is less than or equal to f of x k plus 1 plus gamma k p of x k plus 1, right. Yeah. So, you can bring this here. So, I mean I am just rearranging this to the following. So, I have brought f of x k plus 1 this side and I am going to take gamma k to the other side, gamma k p of x k to the other side. So, you will have this, okay. Yeah. So, but p of x k plus 1 minus p of x k is actually less than or equal to 0 from what we have just proved here, right. So, this is going to be less than or equal to 0, and again that is what we need to prove, f of x k is less than or equal to f of x k plus 1. Okay. All right. So, that is the end of proof. So, let me explain what I have proved in a little more detail. Okay. So, what is happening is that the value of the objective function actually keeps on increasing successive in the successive iterations. Okay. So, this could be coming as a bit of surprise to some of you, because we actually want to minimize f of x, right. So, if you recall, this is the problem that we had. So, minimize f of x subject to yeah, let us say x in S for now, okay, x in some constraint set, right. So, if you only want to find the minimum, how is f of x less than or equal to f of x k less than or equal to f of x k plus 1 help, right. So, what this means is that at x 0 your f was the least, f of at x 1 it has become slightly higher, x 2 it has become even higher, x 3 it has become even higher, and so on. And yeah, if it converges to x star, then at x star it is actually I mean the highest possible value it can attain, right. So, I mean why is that justified? I mean that is something that at least some of you might be thinking, right. So, the reason why this actually happens is because for all the x k's that we are working, okay. So, starting from x 0, x 1 dot dot dot, right, we are actually outside the constraint set, okay. So, I mean if you recall the examples that we looked at, right. So, if just take this example, you have min x 1 plus x 2 subject to x 1 squared plus x 2 squared equal to 1. Okay. So, that was the very first example that we considered, and when gamma is equal to 1, okay, yeah. So, if you recall the answers, I mean, so since we have all the answers here, I mean we will use it to our advantage. So, you can see that we started with minus 1 comma minus 1, right. So, that was x 0. So, at when gamma is equal to 1, the answer was minus 0.809 minus 0.809, right. So, this is actually a point that is outside the constraint set, right. So, 1 by root 2 1 by root 2 is minus 0.707 minus minus 1 by root 2 minus 1 by root 2 is minus 0.707 and minus 0.707. Okay. So, what you have here actually is minus 0.809 and minus 0.809. So, this is obviously outside the constraint set, right, and that is the reason why you see f of x k is less than or equal to f of x k plus 1, right. So, because I mean outside the constraint set your f is actually going to be even lower, right. So, your if f of x k is less than strictly less than f of x k plus 1, what it means is that x k is outside the constraint set. Okay. So, that is the reason why I mean you are actually getting f of x k less than or equal to f of x k plus 1, and you can see the values minus 8.09 minus 8.09 minus 7.628 minus 7.628 minus 7.365 minus 7.365. So, if you take x 1 plus x 2, that is actually increasing gradually. So, here it is minus 1.618, here it will be minus 1. I think 514, and here it is minus 1.473 or something, yeah. So, you can see that it is gradually growing and finally it reaches yeah minus 1.4142, right. So, that is minus root 2, right. So, yeah, so this actually tells us that the value of x from x 0, x 1, x 2 and so on, right, it gradually moves towards the constraint set. It was somewhere outside the constraint set, it slowly moves towards the constraint set, and that is also indicated from this equation where you have p of x k greater than or equal to p of x k plus 1. So, what does it mean? It means that the penalty keeps on coming down, okay, which is what we want, right. So, yeah, I think this is a sufficient result to indicate all of that. And one more thing that you need to note is that f of x k plus gamma k p of x k is less than or equal to f of x star plus gamma k p of x star is the answer, the actual minimizer of f of x subject to the constraint. Okay. And yeah, so since p of x star is 0, right, so all the constraints are satisfied, so no penalty. So, that is actually f of x star, right. So, at every q of x k gamma k, right, you can see that q of x k gamma k is less than or equal to f of x star, and so what it means is that you are somewhere outside and you are slowly moving towards f of x star. Okay. So, this is actually a method where every x 0, x 1, x 2 dot 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 every point is actually outside the constraint set. So, you are approaching the constraint set from outside. So, it is not that you are somewhere inside and you are I mean somehow trying to remain inside the constraint set, that is not what is happening in quadratic penalty method. You are actually outside, somewhere outside, you are gradually coming towards some point in the constraint set, and it turns out that after so many iterations you are actually near the minimum, the minimizer point itself. Okay. So, that is how the method has been designed. Okay. So, yeah, now you can possibly ask what happens if I choose a point. So, initial point is in my hands, right. So, what happens if I choose an initial point that is inside the constraint set. Okay. So, usually it turns out that I mean in the first iteration itself the point moves out of the constraint set. Okay. So, again I will illustrate with an example. Okay. So, yeah, well, let us take the final example that we worked out where we have only inequality constraints, half of x 1 minus 3 the whole squared into half of x 1 minus 2 the x 2 minus 2 the whole squared, where we had a triangle, right. So, coordinates of the triangle was 0 0 1 0 and half half. So, I will take this point just for the sake of it, I am taking half comma 0, okay, and let us see what happens. Yeah, so instead of 3 comma 2, let me pick half comma 0, okay. So, you can see that yeah, I mean the code has not worked because of the first line. The first line is satisfied vacuously because the penalty is 0. So, q of x comma g m minus f of x is 0, okay. So, that can be avoided, I mean, so to correct this fallacy, I am just going to add a simple step. I am going to do this, okay. So, if gamma is equal to 1, that is in the initial step at least I am saying that go inside the loop, okay, do not I mean yeah, since the initial point could be inside the constraint set. So, at least when gamma equal to 1, I am asking the code to work as such. Now, let us see what happens when I run this code. So, you can see that I converge to the answer 1 comma 0, okay. So, if you see what has happened, so yeah, I have started at a point which is inside the constraint set, but what happened after one iteration, I got to the point 1.4 comma 4, which is outside the constraint set because x 1 plus x 2 is less than 1, is a constraint that less than or equal to 1 is a constraint that we want, but here you can see that x 1 plus x 2 is actually greater than 1, right. So, you can see that every point here 1.222 my and 0.222, 1.118, 0.1176, I mean all of this is violating the constraint x 1 plus x 2 greater than I mean less than or equal to 1, right. So, immediately in one step it has gone outside the constraint set, okay. So, actually it is not a problem if x 0 were inside the constraint set, it will very quickly move outside the constraint. So, that is something to remember, okay. I think this actually gives a good understanding of how the method works. I would like to point out two issues in this method before closing our discussion on quadratic penalty method, okay. So, one issue is that you converge the solution all right, not a problem, but you converge the solution only when the value of gamma is very high, okay. You never converge to the solution when gamma is 1, 10, 100. I mean I have never seen an example where I get an answer for gamma equal to 100 or even gamma equal to 1000, okay. So, the values of gamma has been in like hundreds of thousands and 1 million, 10 million, that is the numbers that we usually see. So, you could have seen it from these examples as well, right. So, gamma never converges for so the method quadratic penalty method does not converge for small values of gamma, that never happens, okay. So, that is actually a problem because for high values of gamma the minimization actually is a little difficult, okay. So, that we saw it actually with steepest descent, right. So, when gamma is high the condition number is not close to 1, right. So, it is far away from 1. So, for each instance of the outer loop the inner loop actually takes many iterations to complete, right. So, that is for steepest descent, and even for other methods when you have such high values, I mean imagine when you actually have a function of this such. So, you want to minimize x 1 plus x 2 plus 10 power 6 into x 1 squared plus x 2 squared minus 1 the whole squared, right. So, this 10 power 6 is, I mean it looks very odd, right. I mean this is not what you would expect in a minimization problem, right. So, this is actually a problem with this method, and you cannot correct this because we are actually approximating gamma tends to infinity, right. So, if you recall I think in one of the lectures in this week, right. So, I mentioned that q of x comma gamma is actually an approximation of q tilde of x. Q tilde of x is supposed to be infinity outside the constraint set, right. So, that is the reason you are actually having something like infinity, right. So, outside the constraint, if it is 0 that is going to be 0, but if it is non-zero the penalty is just huge, that is when the answer actually converges to the method actually converges to the right answer, right. So, that is actually one of the very big problems in quadratic penalty method, which is so I will say issues, which is convergence occurs only at very high gamma. Okay. So, that is actually a problem. There is also a second issue that I would like to flag. Okay. So, I will flag it by the following example. Okay. So, this is a trivial example, but I would like to let you know what is happening. Okay. So, let us take this particular problem min x1 squared minus 15 x2 squared subject to the condition that x2 equal to 2. Okay. So, yeah, I mean you never have constraints such as x2 equal to 2. I mean if you had x2 equal to 2, you would say that, yeah, I mean you are just minimizing x1 squared minus 60, right, instead of writing it this way, but I mean this is to drive home a certain point. So, keep that in mind. So, yeah, so this is actually equivalent to, so if you are asked to find the answer, you would do it this way, minimize x1 squared minus 60 over x1, and the answer is just the solution is x1 star equal to 0, right. So, x1 squared is minimized at x1 equal to 0, right. But what happens when you apply quadratic penalty method? So, it is q of x comma gamma, which is x1 squared minus 15 x2 squared plus gamma into x2 minus 2 the whole squared, right. So, that will become x1 squared. So, you have gamma x2 squared, right. So, you have gamma minus 15 into x2 squared. So, gamma x2 squared minus 15 x2 squared has become like this, and minus 4 gamma x2 plus 4 gamma. Okay. So, if you are minimizing this with a gamma less than 15, okay. So, suppose you minimize this, minimize q of x comma gamma with gamma less than 15. Okay. So, you can see that q actually the minimum is actually minus infinity, right, because gamma minus 15 is negative, right. So, you can put x1 equal to 0 and x2 you can drive it to I mean down to infinity, and yeah, so you can see that q of x comma gamma can go as bad as minus infinity, right. So, actually q of x comma gamma, the minimum of q of x comma gamma diverges to minus infinity, right. So, yeah, I mean since this is a simple problem, you actually see what is happening, okay. But I mean you could have such issues for some complicated problems as well, where I mean you start with a gamma and you see that it does not work, right. So, yeah, I mean these are certain issues that you have which has no solution as far as this particular method is concerned. So, yeah, these are drawbacks of this particular method, and that is the reason we are actually going to the next method, which is the augmented Lagrangian method. Okay. So, we will learn about that method from the next week. Okay. So, yeah, I think this is a good time to stop for this particular week on quadratic penalty method. Thank you.